Good morning and welcome to this Automation Academy Mastering the Machine webinar for the 7th of October 2023. Today's topic is troubleshooting in PLC platforms, troubleshooting and cross-referencing. Hope you enjoy it. Good morning folks and welcome to Mastering the Machine. This is webinar number 64, the 7th of October 2023. And we're going to be covering PLC troubleshooting and cross-referencing today using Allen-Bradley and Siemens platforms. Before we get into that, a little bit about the Automation Academy itself. This is a membership website that I have opened up for training, PLC training, systems integration training, that sort of thing. There are a lot of training videos for different PLC platforms on the website, some job and aptitude assistance taken from Ken Coleman's program, lots of documents, big library of training and technical documents, a little bit of software on there for PLC programming, some Beckhoff material, fairly new Beckhoff material, new video on PID using Allen-Bradley's ControlLogix platform. Several programs on there. We do have a community with some interest groups on it, IO Central, and we do have these regular events, the Mastering the Machine webinars, about every 2 to 3 weeks. And this was named after the document you see there in the upper left-hand corner. It's named Mastering the Machine, and you can find that at automationllc.com or on the Automation Primer. So as I mentioned, today we're going to be using two different PLC platforms here. We're going to be using Siemens old Step 7 and new TIA Portal, and we're going to be using Allen-Bradley's RS-Logix 500 and the newer ControlLogix platform. We're going to be using Studio 5000 for that. So without any further ado, I'm going to go ahead and bring up a remote desktop that I have set up here with all four platforms on it. And we're going to start out here with Siemens Step 7. For those who haven't seen Siemens Step 7, this can be a little bit bewildering. Sometimes there are a lot of different windows that will open on top of each other. So we're going to go in here and quickly take a look at the blocks that are in this program. This particular program I use in some of the training classes for automation training, and what the students do is they will go and answer questions in the book, tracing, for instance, take an output and trace what might cause that output to not operate correctly. So we're just going to pick something random here. OB1's not that random, actually. OB1 is the main routine that starts running immediately. And I'm going to open it up here. And what you're going to notice is, yes, this is a completely separate window, right? You have the manager here, and then you have the program itself. And you'll notice that this particular program is shown not in ladder logic, as you might be familiar with, but in something called statement list. And statement list is a version of instruction list that Siemens has kind of put on steroids. So a very powerful text-based program similar to assembly language. So from here, I can open up my reference data, which is a lot of what we're talking about today. And when you do this, you'll get a choice. It'll say, do you want to open the cross-references themselves, or for instance, the assignment list, the program structure. And it doesn't matter which one of these you open, because from the window that opens, you'll be able to get to all of the other choices also. So we'll start out here, for instance, with the assignment list. And the assignment list shows everything that was used in the program in alphabetical order. So you can see here, and I have no filter on this, so you can see the inputs listed here, you can see the outputs listed here. And what you see out here to the right is that some of these things were addressed not as individual bits where these X's are shown, but as whole words or bytes, right? So these MBs You can see here this is a memory word. This would be known as memory word 2. And that might be important because, for instance, here, this output byte was addressed as an entire byte for one reason or another. I believe this was used in a fault in the program, but you can see also the bits were used here. So from here, you can see what was used, and we're just going to kind of pick something randomly here. So I'm going to go into the cross-reference, and now everything's in here in alphabetical order. And I'm going to do kind of like we would do in the class, right? Just pick an output and say what causes that output to operate. So let's say I'm in here in Q5.2, which is one of the outputs, is not operating correctly. So the place that I want to look for the output is I want to look for its coil. And for Siemens, the coil is signified by an equal sign. So if I go in here, and this is whether it's in ladder or it's in statement list, and you'll notice a couple things. One, there are no comments in here. So this program was taken from a PLC, and the symbols were not imported. So there are no names for anything, and that would make things really tough if you were cross-referencing. But let's say you had a set of electrical drawings, and I go through the electrical drawings, and this is one of the outputs that I want, and it's not operating correctly. Let's see, this is 8.2. I think I wanted 5.4, I believe was what I picked. Let's go back to the reference data. See if we can find that. There's my cross-references. And Q5.4, if I open this up, there's the coil that I wanted. So now I'm looking for the coil of 5.4. I open it and it goes to it. So here is an output that is controlled by these different bits. So the typical thing to do here, and you would probably want to take out a nice little notepad, piece of paper, something like that, to write down all these different locations. So let's say I'm approaching this from scratch, and I'm going to get my own little piece of paper out here, and I'm going to write down, in this case, network 2 and FC14. So that is function 14, network 2. And the thing that I'm looking for is what makes Q5.4 operate. So Q5.4, maybe I go up to it and it's supposed to be on, but it's not on. So I'm looking at the logic here. And if I were online, of course, I could tell which of these bits were true or not. And I'm just going to pick one of these. So for instance, this address right here, db11.dbx 144.0, I can right click on it and say go to. So I could say go to location, and it will open up all the places where that address is. And you can see here the only places where that is are read only, right? So they are reset. And we'll go to one just for fun here. Since they're in a different routine, it opened it up here. And you can see this data block, only the bit itself is showing here, not what actually changed it. So the thing that I would want is the right bit, the thing that actually changes that bit. So I'm looking at this, and what a data block is it's a giant collection of data. And so this is a little bit of a complex example to start out with, right? Starting out with a data block. But basically what a data block is a whole bunch of different information, and that data block could have been addressed as a whole. So I could have taken that entire data block and moved it into a location. And so I would have to go to data block 11 and see everywhere that might have written to data block 11. Again, alphabetical order. I'm going to change the filtering here and say I want to see everything, which will enable these data blocks. And say OK. And now all of a sudden the data block itself, data block 11, would be shown. And the thing that I'm looking for is a write type of address rather than a read type of address. And what this is, here is a load, and here is a transfer. So transfers are write type of addresses rather than reads. So here's a whole bunch of DB11s. Notice once again I have a completely separate window open here, so this is complex. But that's where I would start looking for, okay, what could have changed DB11, and we'll go back here, DB11.dbx144. dbx144 is an individual bit within DB11. I could also go into my usage table that I was at before, and I could look at the entire word and find out what changed that. So I think what we're going to do is we'll look at DB11. We'll go ahead and show you that if I go to this, it will go to the location at which it changed. What this did is it took 0 and it transferred it to db11.datablock_byte270, and it wiped it out. So it wrote a 0 to it and changed that entire byte all at once. And the rest of these DBBs would do the same thing. So that's a more difficult example. Let's take a simple example. So this example, this is just a general memory bit, and I'm going to right click on it, and I'm going to do the same thing, go to location, and it's going to show where did that bit change. That bit also could have changed with an entire word, but in this case we find a coil. So we're going to use that as our example. I'm going to double click it, it'll go to it, and you see this coil. And I'm going to write this down. Once again, I don't have any kind of bookmarks or anything, so I'm just going to write this down. I'm going to say FC25, and this is network 4, and this is where the coil is. So I may want to create my own shorthand here, put a little equal sign, and then put M143.3, and the things that change it are M70.2 and M70.1. So you see what I'm doing here. If either one of these bits, M70.2 or M70.1, did not come on, then neither would M143.3, and that of course would also mean that Q5.4 did not come on. So I don't know if you can see my screen here, but this is the little notepad that I have, and I have a trace of everything that I've been looking for. Just for fun, we will trace this one further. I'll say go to M70.1, and once again I find 2 write commands, right? These are, for those of you who do Allen-Bradley, they're called destructive bits. Rather than just reading the bit, they are writes, and this one sets it and this one resets it. Let's say I was expecting for it to be set, so I'm going to go to it. We're into FC17 here. I write it down. I see FC17 network. Looks like there's the set. Network 13 has a coil, and it is operated by a few things. Notice I'm out a ladder here at this point, so that's one of the things about Siemens that you would have to learn, which is statement list. Statement list is really the equivalent of ladder. In this case, for me to read this, it would say if T25 is true, this is and T25, it's just a contact, then reset M70.1, and if also T26 is true or I12.2 is true, then set M70.1. So it looks like we found both our set and our reset here. So a lot of times if I'm teaching a class like this, I'll say just trace this a few steps back and until you hit an input. All traces will end up in one of two places. Either a physical input, which is changed by electricity, right? Or a bit or a word that doesn't seem to have its origin anywhere in the program. What does that mean? That means it came from somewhere outside. An example of something outside might be an HMI, right? A push button or something like that on an HMI. It might be a remote PLC that took an entire word worth of data or a block full of data and wrote it the memory into that data block. Could have come from somewhere else. But I'll always run into one of two things. I'll either run into some kind of a physical input, or I'll run into something that doesn't have a write command in the PLC. So be careful if you don't find a write command in the PLC. Look at whole words or whole blocks that might be affected. An example would have been that data block. So in this case here, we'll say I'm looking at my program and I notice that I12.2 is not on, and we'll say I12.2, and I go and I figure out why isn't I12.2 on, and maybe it's a sensor that is bad or something like that. So that's a little bit of an example of how to do it in step 7. This is probably the most difficult example that we're going to go through today. So you see all these different blocks that opened up. You see that the Semantic Manager is open and the cross-reference is open. From the cross-reference, I can get at pretty much anything. I can see whether things were used. I can see where they appear. I can even go in and look at bits that unused symbols. Well, in this case, I have no symbols, right? So I have lots of unused symbols, everything pretty much. And then I have addresses without symbols, which are basically everything. So that's a little bit of a look at Siemens Step 7. So what I'm going to do here is close some of these things. This can get confusing. That's kind of why I started out with Siemens Step 7, because you can have a whole lot of windows open, right? So we went through OB1, which called these other things, then FC 13, 14, 28. All these things are open in the editor, right? So I'm going to close the editor. I'm going to close the cross-reference. I'm going to close this little go-to window here, right? And of course, I can also search and do other things within here. But Siemens Step 7, it's an older platform, and it's one of the more difficult things to understand, right? So that class is a little more difficult class than some other ones. So we're going to minimize this. And this time we're going to open TIA Portal. So this is also a class exercise that I use in classes to go through, and this is called First Start. And once again, the names and everything in here are more or less the same thing. So I have an OB1 that calls everything else. I can look at call structure and things like that. We'll just open one of them up. That'll show you a little bit of the editor. Okay, so once again, I have the ability to use statement list, and I have the ability to use ladder. This was written in ladder, so I have an empty rung here, but then I have some statement list after it. A lot of times your statement list is things that can't be converted into ladder. So in this case, I have one network with a whole lot of calls in it, a whole lot of equal signs and things like that. So once again, we're going to pick something and trace it. And we'll see if we can find something randomly here. Maybe we'll do a search, or just take a look at the reference data in this program. So here I'm right-clicking on one of the blocks, and I'm saying take a look at the cross-references for this, cross-reference information. And once again, just like regular Step 7, I can look at the assignment list, and then from the assignment list, I should be able to open the cross-references. So these are things that have been used, and in this case, we'll just pick, again, a queue, and we'll say this queue didn't operate correctly. There are no filters in here. Looks like I don't have any queues that were used in this particular output. We'll pick this. So this is a cross-reference for a bunch of inputs, outputs, things like that. And I'm just going to pick one here. And notice that I'm only looking at FC1. If I go up here and I say cross-references, I should get everything in my program blocks. So once again, scrolling down, I can see all of my FCs and everything here. What I'm not seeing is all of my Qs. So here I right-clicked on Station 4 and I find a list of everything in Station 4 that has a Q assigned to it. If I open up any one of those, I will see which blocks they were mentioned in, and we're just going to kind of pick one here. I'm going to say here is a coil. This is also in statement list, just like step 7 was. So Q5.5, what are the things that affect Q5.5? And I have the ability here to once again write down which block I found this in. And in this case, this is FC14, and that's the coil. So I'm going to write down an equal and Q5.5. All of these different addresses could have changed that. If I looked at this and I said, well, I'm expecting for the filler to be running and I0.4 should have been on, but it's not, then I'm done with my search, right? But we're going to go a little bit farther here and pick something else, just so we get a little practice tracing. The way to read this, once again, statement list is a little tricky, but this is saying if I0.4 is on and M130.2 is on, or 142.1 is on, or 156.4 is on, any one of those, and right, this data block is on. And a lot of times these data blocks are things like recipes or conditions to allow the output to come on, or data block 11, stat 199. Notice these don't have any symbols associated with them. That makes it a little harder for students to get through this. But once again, I'm just going to pick one of these, and we're going to say go to this address, and I can say next point of use or previous point of use. I couldn't find it in the next point of use, so we'll go to the previous point of use, or the cross-reference information in general. I can go down here to the bottom, and I can see everywhere that was, and I can find my right. So here is where undefined marker 144 was written to. This is the coil, and I double-clicked it and I went to it. So at this point I am in FC25 network 3. And if I look at the logic up to this point, counter 16 has to be up to 20, and once again the filler has to be running. So we'll assume here that the filler was running, but the counter wasn't up to 20 yet, which was going to mean that that output wasn't there yet. So now I click on counter 15. I'm back down here looking at the cross-reference and finding out where this counter counts at. And a lot of times if you look right in the rung before this, you'll actually find the counter. That's just a logical thing for programmers to do. A lot of times you'll find the counter here, but let's say you cross-referenced it and you landed here, and you can see that Q5.4 has to be off, right? This is a normally closed for Q5.4, and I5.0 has to be true. So once again, kind of a difficult example because we're in statement list and because we don't have any symbols. So I search for I5.0 and write down what I was looking for, which was, let's see, I write 142, M142.1. And you'll trace this back as far as you need to, right? And that was in network 3, and then when I went to network 2, I found a counter. The counter was counter 16. And counter 16 is made to count by I5.0, and Q5.4 has to not be on. So we don't have names for these, but let's say I trace I5.0, and indeed that is a bad sensor or something like that that was not allowing my counter to count. So you'll trace it back until whatever you're looking for kind of appears here. So this can take a little bit of time. So maintenance people have to fight through this stuff. So network 2 was counter 16, and I found that I5.0. And then I might, in my plant, have a something that I need to write down saying I5.0, which was such and such a sensor, was bad. So I have to go get a new one and wire it back into the system, test the system, start it back up, and I'm good to go. So that's a little bit of a look here at statement list, and that always, again, we teach this class in TI Portal in ladder logic, but then all of a sudden they're throwing into statement list and have to interpret this logic. So once again, you may have to learn another language to be able to successfully cross-reference things. So that was a little bit of a look at Siemens TI Portal's cross-referencing tools. You both have this cross-reference down here, and of course, as I mentioned before, you can look at the assignment list, see what was used in the assignments. You can look for symbols and things like that, usually cross-reference from the symbol itself, and hopefully, if what you understand is ladder and your program's written in ladder, you'll be able to trace things down. So that's a little bit of an example there of Siemens. Now we're going to move on to RS Logix 500. This particular program is not an example program. This is a real program that was actually running in Miami in the jobs that I do down there. So here you don't have necessarily just a cross-reference tool for your inputs and things like that. In this case, I have a device net module, right? And the device net module was bringing all of my I/O into the program. So the things that I'm going to program are not going to be regular I/O, right? So that also makes things a little bit tricky. I happen to know some things about this program, and there are comments on here. You can see that there's nice always on and always off. So hopefully tracing this out, let's see, registration may have some of the outputs. I know that alarm has some of the outputs. So we'll find something like one of these tanks, right? These are tank 3, that sort of thing. I have a lot of valves and high-level sensors and low-level sensors and things like that. The ACT is actuators. So in this case, if I go into the actuator routine, I'm going to find some of my valves and things like that. So here is a command to turn on a motor. And this command goes into the device net routine and then is mapped as a output, right? So QB is a Q bit for M21, which happens to be a motor. So this motor will run if all of these things are true. And this is a pretty complex rung for ladder logic, but you have to deal with what's there. So I'm going to spread this out. Allen-Bradley's rungs kind of fold in on themselves. And you can see here, if the volume on the agitator is above this, and this timer is between 0 and 300, and I'm not in step 1 of CIP, and you'll see a whole lot of that down here, and I'm not in held status. If I were in held status, this would also go off. And in this case here, I could look at this logic and I could say the reason that this is not running here maybe is this bit. So I'm going to cross-reference this bit. So I go to cross-reference here, and I get a list of wherever that bit was. And once again, I am looking for the right bit. So these are all examine if closed. This is an examine if open. And in this case, I also have these decodes, which take and change the entire word. I'm not finding an individual bit here, but I will find whole words rather, for these. So if I look to N7 or N14 64, I find the decode right here, and I'll find one of those. This is the thing that changes this. So I'm going to go to it, and here is where, if this N74:0, right, is between this, what decode does is it takes an individual bit and it decodes that into a hex number. So I take individual bits and I will turn it into a number. And that's what's going on here. So you can see here that there's a 1 in this bit. So I took a hex 1 and I moved it into here. It's just decoding it, and if I had a hex 2, then I would have put that into here. And so this is, again, a little bit complicated by the fact that all of our I/O is mapped into here. But I can also cross-reference back and find out what makes N764 change. And in this case, it's N74:0, whatever's in there. So once again, cross-reference, find out where this changes. Here is a move, right? A move can go two ways. I could have moved this number into something else, or I could have moved something into this number. So once again, N74:0. And here are some of the individual bits that make that happen. This will move a 0 into this bit. Sometimes I'll find after that, into this word rather, something will move a 1 into this word, a 2 into this word, and such. So I'm tracing down through here, and you'll see that a lot of this stuff, right, is a sequence, and it steps through 1, 2, 3, 4, such, and I can see what step of my sequence I'm in. And I can see that I don't have a start recipe command yet. Everything else looks like it's okay, but I haven't gotten this. Well, where does this come from? Once again, cross-reference. And here is the first place where I actually find an individual coil. So once again, I would be writing all this down as I go through here. I find out that my start recipe comes from all these different conditions listed in here. Menu ID, function ID, control ID, all this stuff has to be in this condition, and you can see it's not. So in this case, once again, I happen to know that this program interfaced with an RSView32 HMI, which is basically SCADA. It was a computer, and as people selected recipes and things, they would select a menu number and a function number and a control ID, and it would change these numbers on the HMI, and then that would issue the order to start the recipe. So somebody's sitting here manipulating the start recipe screen, and as they set these different numbers, then this command would go into the N14 register, get decoded, turn it from hexadecimal into individual bits, and then that individual bit would make something happen. So that's, again, a little bit complex look at RS Logix 500 and some of the things that you might have to follow in a program like that. So this is, again, a very difficult cross-referencing application. But individual coils, in this case, this COM RS view is all coming from the SCADA system, but I have all these different blocks open. I can see the logic that is stopping this number from going into this location. I can right click on things and find out what turns them on, what makes the status stopped, things like that. My sensors in this case are pretty much all labeled. You know, I have addresses for GS switches and things like that. So I can tell whether inputs are made or not, and they are actually referenced into, once again, DeviceNet addresses and things like that. So I've looked at some pretty complex things here as far as these are concerned, just to kind of illustrate how cross-referencing a lot of times will depend on entire words worth of data rather than individual bits. So this is a kind of an advanced lesson here. The next one I'm going to make a little simpler. I'm going to pick control logics, and control logics has a few things that make things a little bit easier to cross-reference. One thing is they have something called bookmarks. So as I'm going through a program, and for instance, I'm just going to pick something random here. Here is a pick and place, or a load pick and place. I'll pick that. And here I have a pretty straightforward sequence, right? And something's not happening. I also have some output routines, so we'll open that up also here. And the bookmarks bar is right up here. And so instead of writing things down, I can actually put check marks by these and then step through all these different locations. These are also something that makes this much easier, and I'm going to go through this as kind of the main, your typical troubleshooting exercise. If I have an output that has failed to operate here, so for instance, this is a pick and place. This has got a nice symbol. It says load pick and place, X-axis retract solenoid valve. This is not operational, and it could be not operational because the permissive was not made, right? In which case, for instance, turn this off. We'll toggle the bits. And you can see this permissive then would be off. If this is not made, but I'm in auto mode, right, and my retract command is on, we'll just toggle that again on. It looks to me like this permissive is not made, so I would need to go trace these, and in this case I'm not going to have to trace it very far. That's a good thing. Go to cross-reference for this, and I find all the different places where this is mentioned. There is only one here that is a write bit, and you can see here that this is a something, sometimes people call this a DI handler at Automation NTH, for instance, and it takes the combination of these two sensors, and in this case this is the raise status, and it says that the raise needs to be on and the lower needs to be off. And I can look here and I can see that it is, right? So in this case, this status should have been on. Of course, I'm not online. I'm just going to type a 1 in there. I'm going to go back to my routine, and I'll see that if this was on, this would have been on here also. So looks like everything's ready to turn this on, right? This would have been on. So tracing things, that's very much the way that works. In this case, we're going to pick something a little different. We're going to say the x-axis failed to extend. And the reason that it failed to extend, it looks like all the permissives are there. Everything's okay. I'm raised, but I did not get this command. So I'm going to once again go to the reference data for this and find the destructive bit. So this is a writable command, right? It's destructive. And so I'm going to go to it. Before I actually do that, I'm going to go back to these outputs and I'm going to bookmark this, right? So I just put a bookmark here, and then I go to the cross-reference and I find this sequence. I'm going to bookmark this also. So this just saves you from having to write things down. So if I'm between steps 40 and 70 of the sequence, then this would be on, and instead I'm getting a retract. And now I can go to the sequence itself, go to cross-reference for that, and I'll find a whole bunch of equals and moves. And as those of you who followed how sequences work, these are all moving different numbers, right? So you see that the rungs are in order. I've got, rung 4, rung 5, rung 6, and they're all in the same routine. So I'm just going to pick one, and I'm going to say, why, for instance, did I not go from step 20 to step 30? And you can look at the logic here and see why I didn't go to that step. And in this case, for instance, I'm not even in auto cycle. In some cases, I can look at the sensors directly. In this case, I'm in dry cycle, right? So we'll just kind of turn those off for education here, and we'll say I'm in step 20. So we'll type that in, and I'm failing to go to 30. It looks like I haven't hit this prox, but if I'm not in auto cycle, then of course I won't hit this prox. What makes this prox close? Well, I have to be in step 20, and then I should be getting an output firing that turns this prox on. But in this case, we'll just go ahead and trace this back to auto cycle. What puts us in auto cycle? Go to cross-reference. Once again, what do I want to look for? I want to look for a writable bit. I have a unlatch, I have a latch, and in this case, I'm going to go to the latch. And the thing that puts me in auto cycle is somebody has to push the auto cycle start push button for 3 seconds. I will get a start signal, and when the timer's done, I will latch in auto cycle, and that would put me in auto cycle, and then I'd be running. So that is a little bit of a look at all these different things. Put another bookmark here and show you how those work. Once you have bookmarks in these locations, you can toggle from bookmark to bookmark. So this was a lot easier than writing things down. Right, so that's a look at the different cross-referencing tools in all these different platforms. So this is ControlLogix. It's pretty much the easiest of all of them, but in most cases for simple programs, the philosophy is going to be the same in this case. For instance, I have an output. I go to a command that tells this output to happen, cross-reference it. It will take me to some location where I can find a nice coil. Right, in this case, I'm looking for this output. I'm looking for the coil. And I can find that I should be between steps 40 and 70, so this is not on. So what stopped me from getting to 40, I happen to know I can just scroll up, but I could also go through these bookmarks, and I will get back to it. Or I can use a sheet of paper like this and just list things out and then go from step to step. So if you don't have bookmarks, your next best bet is to write things down and just follow the bits, usually starting from an output bit and then looking at the conditions of the machines. So these were some pretty complex examples of how to do this. Hopefully you will have easier examples. So that was a kind of a look at everything that we needed to look at here. The next webinar will probably be on October 29th, and I'm really hoping to get Jerry Wassinger from Pipeplates on here and maybe talk to him and Phil Scruggs again about the new products in Pipeplates, maybe even Mike O'Day, who's been on here before also, and take a look at some of the new things Jerry's doing. He's got actually a new controller that looks like a Raspberry Pi of some kind, and he's marketing that controller along with his Pipeplates. So that's pretty much it for me today. Hope you enjoyed the webinar. It was a little bit complex, but you got to see a little bit of the cross-referencing tools in the Siemens and the Allen-Bradley platforms. Hope you enjoyed it.